In this video, we will be talking about logarithmic functions and their graphs. Before we get to that, there are a couple of things we need to recall. The first are inverse functions, which is what we went over during the first chapter. Very basically, an inverse function is something that undoes its original. So if we have the example y is equal to 4x minus 5 divided by 7, in order to find the inverse, we swap the x variable and the y variable, and then we just solve for y. So when we do that, we'd have to multiply both sides by 7 in this case, so we'd get 7x is equal to 4y minus 5. We'd add 5 to both sides, and then we would divide everything by 4. So in this example, this function undoes this function, and vice versa. The other thing we need to recall are exponential functions and their general idea. We need to know the terminology, so if we have f of x is equal to a to the power of x, we need to know that a is the base and x is the exponent. And we generally need to know what the graph looks like. We also need to know the one-to-one property. So, for example, if we have 3 to the power of x plus 4 is equal to 9, we can rewrite this as 3 to the power of x plus 4 is equal to 3 squared. Because there are the same bases on both sides, they basically cancel. So then we have x plus 4 is equal to 2, so x is equal to negative 2. We also need to recall that we have two very important equations used in the growth of money. Okay, so we have a is equal to p e to the rt, and a is equal to p times 1 plus r over n to the n times t power. The first one is the continuous function, and the second one is compounding a certain number of times a year. The last thing we should really know are the properties of exponents. Specifically, these two I have written here. We need to know that anything to the 0 power is going to be 1. So if we have 5 to the 0 power, that's just equal to 1. We also need to know about fractional exponents. So if we have a to the 1 over b power, that's the same thing as b, the b root of a. So it's asking how many times multiplied by itself do we get a. So for example, if we have 4 to the 1/2 power, that is really the second root of 4. So 4 is something multiplied by itself twice. In that case, it's just 2. That's also rewritten as just the square root of 4, which we just know is equal to 2. So what are logarithmic functions? Very basically, logarithmic functions are the inverse of exponential functions. And the general definition goes as follows. For x is greater than 0, a is greater than 0, and a is not equal to 1, y is equal to log base a of x if and only if x is equal to a to the power of y. Both of these equations are the same thing. They say the exact same thing. And we need to be able to switch certain functions into the other. So we need to take a logarithmic function and switch it to exponential. And we need to be able to take exponential functions and switch them into logarithmic functions. So for example, if we have log base 2 of 32, that is asking 2 to what power gives you 32. So we can rewrite this function as 2 to some power is equal to 32. And if we were to solve that, x would be 5, because 2 to the 5th power gives you 32. In the next example, log base 3 of 1 is asking you 3 to what power gives you 1. So again, we can rewrite that as 3 to some power is equal to 1. Because anything to the 0 power gives you 1, x has to be 0. In the next example, log base 4 of 2 says 4 to what power gives you 2. So we can rewrite that as 4 to some power is equal to 2. In this case, we're going to need a fractional exponent. So 2 squared is 4, so 4 to the 1/2 is 2. So x will equal 1/2. We can also rewrite this using the one-to-one property as 2 squared to the power of x will equal 2 to the first. So 2 to the 2x will equal 2 to the first. And again, because we have the same base on each side, they cancel. So 2x will equal to 1, and x will equal to 1/2. These are the same. These are different ways to do the same thing. And lastly, when a log has no base attached to it, it is assumed to be base 10. So if we have log base 100, that is the same thing as saying log base 10 of 100. Which again, if we rewrite that, that says 10 to some power is equal to 100. And we know that 10 squared is 100, so x will equal 2. Just as exponents have properties, so too do logs. And the ones that we need to know for now are the following. So log base a of 1 is equal to 0. Again, if we rewrite that in exponential form, that says that a to the 0 power is equal to 1, which is always true. The next thing we need to know is that log base a of a is equal to 1, because, again, if we rewrite that in exponential form, a to the power of 1 will always equal a. The next one takes into account that exponential equations and logarithmic equations are inverses of one another. So if we have log base a of a to some power, we're just left with that exponent. So log base a of a to the x just leaves x. In a way, these two bases cancel. It also says that a to the power of log base a of x will also leave x. Again, because these two bases will cancel each other out. The next is very similar to what we went over with the one-to-one property. So if we have log base a of x, and that is equal to log base a of y, so long as they have the same base, then we know that x must equal y. So a couple of examples. The first, log base 4 of 1. If we rewrite this, that says that 4 to some power will equal 1. Again, if we know our properties of exponents, then that means that x must be 0. The next example, log base root 7 of root 7. Because these are the same bases, they cancel each other out, and we will just get 1. If we rewrite that as exponential, this says that root 7 to some power will equal root 7. And the only number that does that is 1. In the next example, we have 6 to the power of log base 6 of 20. Again, because these bases are the same, they cancel. So we're just left with 20. In red, we have the one-to-one property examples. So the first one says that log base 3 of x is equal to log base 3 of 12. Because both sides have the same base, x must equal y. And in this case, y is 12, so x must equal 12. In the next example, we have log base 10, because there is no base, of 2x plus 1 is equal to log of 3x. Again, because they have the same base, we know their insides must be equal. So in this case, we can just set 2x plus 1 equal to 3x and solve as we normally would. So if we subtract 2x from both sides, we get 1 is equal to x. In the last example, we have log base 4 of x squared minus 6 is equal to log base 4 of 10. Again, because they have the same base, we can assume that their insides are equal. So we can ignore the log base 4 on both sides, and we can set x squared minus 6 equal to 10. If we solve that, we can add 6 to both sides, so x squared will equal 16, so x will equal plus or minus 4. The next thing we need to take a look at are the graphs of logarithmic functions. And if you remember from when we went over exponential functions, we graphed y is equal to 2 to the power of x. And just like if we were in 8th grade or Algebra 1, in order to get the general shape of a graph, we can plug in values of x and get values of y for different points. So when we did that for y is equal to 2 to the power of x, when we plugged in negative 2, we get 2 to the power of negative 2, which is equal to 1 over 2 squared, which is equal to 1/4. When we plug in negative 1, we get 1 over 2. When we plug in 0, we get 1. When we plug in 1, we get 2. When we plug in 2, we get 2 squared, which is just 4. And when we plug in 3, we get 2 to the third, which is 8. Because exponential functions and logarithmic functions are inverses of one another, all we have to do for this set of points is to flip where the x and y are. So in logarithmic functions, our y column is our old x column, and our x column is our old y column. So when we plug in 1/4, we would get negative 2. When we plug in 1/2, we would get negative 1. When we plug in 1, we would get 0. When we plug in 2, we would get 1. When we plug in 4, we would get 2. And when we plug in 8, we would get 3. So when we graph that for the exponential, we can plot those points. So our exponential function will look something like in blue, where it never actually crosses the x-axis, but it goes up super, super steep. Our logarithmic function will be the inverse of that. So instead of running along the x-axis and never actually touching it, it'll run along the y-axis. And it'll look something like what I have in red. Now what we need to know for logarithmic functions, as well as exponential functions, is that the rules of transformation still apply, and that these are the general shapes of each of those graphs. As a reference to the rules of transformations, this is directly from our notes from chapter 1. And the general rule for transformations is if it has to do with the outside of the parentheses, you are moving up and down. If it has to do with the inside of the parentheses, you are moving left and right. So when we add something to our graph, we are moving it up that number of units. When we are subtracting something from a graph, we are moving it down. When we are subtracting from the input, we're going to go right, and when we are adding to the input, we move left. When we stick a negative out front and multiply the entire thing by negative, we flip it upside down. And when we add a negative to the input, we flip it left to right. And again, these are examples straight from our notes from the first chapter. So let's quickly practice these transformation rules on logarithms. So graphed in white, we have the parent function log of x. If I ask you to graph the log of x minus 1, we take our function, this white graph, and we just shift it to the right 1 unit. So our function, instead of in white, will look something like this. Then, if we have log of x plus 3, all we're doing is taking our white, our parent function, and shifting it up 3 units. And all of the transformation rules still apply. So if we stuck a negative on the outside, it would be flipped upside down. If we stuck a negative on the inside, it would be going to the left. and everything in between. The last thing in this lesson are natural logarithms. And natural logarithms are the exact same as regular logarithms, except we have a base of e. So a natural logarithm is f of x is equal to log base e of x. We can rewrite that as ln of x, which is what we will be using from now on. And all the properties of log still apply. So the natural log of 1 will always be equal to 0 because e to the 0 power is 1. The natural log of e is 1 because e to the power of 1 will always give you e. And the natural log of e to the x will always leave you x, and e to the power of the natural log of x will also leave you x. Again, because these bases would cancel. And then the one-to-one property also still applies. So if we have the natural log of x is equal to the natural log of y, then x must be equal to y. So a couple of things to review. And all of these examples that we're going to go over are exercises from 3.2. So the first set that I would like to take a look at are directions that say write the logarithmic equation in exponential form. So number 7 says log base 4 of 16 is equal to 2, and we need to rewrite that in exponential form. We can do that by taking 4 to the power of 2, which is equal to 16. Number 9 says log base 9 of 1 over 81 is equal to negative 2. This statement in logarithmic form, or in exponential form, will look like 9 to negative 2 is equal to 1 over 81. And then number 10 says log 1 over 1000 is equal to negative 3. So because there is no base, it is assumed to be 10. So we can rewrite this as 10 to the power of negative 3 is equal to 1 over 1000. The next set of directions say to write the exponential equation in logarithmic form. So number 15 says 5 cubed is 125. We can rewrite that as log base 5 of 125 is equal to 3. Number 17, 81 to the 1/4 power is 3. We can rewrite that as log base 81 of 3 is equal to 1/4. Number 19 says 6 to the power of negative 2 is equal to 1 over 36, which again we can rewrite as log base 6 of 1 over 36 is equal to negative 2. Keep in mind while you are doing these that the base in exponential form is always the base in logarithmic form. The next set of directions say to use the properties of logarithms in order to simplify. So number 3 says log base 11 of 11 to the 7th, and we need to simplify that. So because the base in the log is the same as the base in parentheses, those cancel, and we're just left with 7. Number 34, log base 33.2 of 1. We can rewrite that as 3.2 to some power is equal to 1, and we know that x must be 0. Then 36, 9 to the power of log base 9 of 15. Because the base in the exponent is the same as the base in the log, those cancel, and we're just left with 15. In terms of natural logarithms, we have the following examples. So number 51 says to write the logarithmic equation in exponential form. And number 51 says the natural log of 1/2 is equal to negative 0.693. So because we're dealing with the natural log, we know the base is e, and to the power of negative 0.693 will equal 1/2. Number 58, the natural log of e is equal to 1. Because the base is e to the power of 1 will also equal e. And that's using one of the properties as well. 59 to 65 say to write the exponential equation in logarithmic form. So 59 says e to the fourth power is equal to 54.598, and so on. We can rewrite that as the natural log of 54.598 will equal 4. Again, this natural log assumes e as the base. Number 64, e to the negative 4.1 is equal to 0.0165. Again, because the base is e, we can use a natural log. And the natural log of 0.0165 will equal negative 4.1. Number 65, e to the power of x is equal to 4. We can rewrite that as the natural log of 4 is equal to x. And then 88 and 92 say to just solve. So 88 says log of 5x plus 3 is equal to log of 12. Because these have the same base, which are assumed to be 10, we can ignore the logs entirely and just set 5x plus 3 equal to 12. And when we solve that, 5x will be 9, and x will be 9/5. Number 92, the natural log of x squared minus x is equal to the natural log of 6. Again, because we have the same base log on both sides, we can ignore them and just set x squared minus x equal to 6. And when we solve that, we can get 6 over to the left. And then we can use the quadratic formula. We can solve by factoring. We can use our calculator. I know that x squared minus x minus 6 can factor into x minus 3 times x minus 2. And if we set both of those factors equal to 0, we get x is equal to 3 and x is equal to 2. And this 2 should be plus, so this should be minus. These are all examples from the book, and they cover everything that's in this video. But just some key items to keep in mind. So 1, we need to know how to change logarithmic form to exponential and exponential to logarithmic. We also need to know that they're inverses of one another and they undo one another. Besides that, we need to know what the graph looks like, which we have a new parent function, and we need to know the properties of logs and the properties of natural logs and what that actually means. So far, this is all we need to know as of right now about logarithms and natural logarithms.